Hello, physics friends, and welcome to Chapter 3, which is entitled Accelerated Motion. This specific lesson, 3.1, we're going to define acceleration, we're going to define instantaneous acceleration, and we're going to define average acceleration. And to get us started today, what I wanted to do, I wanted to show you this guy right here. This is called a top fuel dragster. They have the largest acceleration on planet Earth. Like above planet Earth, you can get, other weird accelerations, but when you're riding on the surface, nothing accelerates faster than one of these guys. I just wanted to show you a couple videos here. This first one is a top fuel dragster in slow motion. The amount of horsepower these things have, they wrinkle the tires right here. It's just, there's so many facts that are in these cars. I just wanted to share a few of them with you. Just nuts how there's just much raw power. They consume 11 gallons of fuel per second. Like every 1 second that goes by, there goes 11. I don't think I could dump out fuel fast enough to make 11 gallons dump out. I mean, there's the pumps and just the mechanics that are behind this thing are just insane. I've got another video here that if you want, I'm going to put a link to it, but it shows exactly how these things work. It's really incredible.
17 gallons of rocket fuel. 8,000 horsepower. A top fuel dragster accelerates faster than any other ground vehicle on Earth. It generates 5 Gs and hits 300 miles per hour in the time it takes a conventional car to go from 0 to 30. How do these amazing machines convert all that power?
Now, I don't know if you saw this.
From 0 to 30.
Their face.
How do these amazing machines?
Right here. See this little tether? They physically have to chain the racer's face down because when they hit the gas, their head wants to go back and they can't see down the race course, so they have to physically chain and then tighten up this strap right here to get him to see down the racetrack. I just want to share with you a couple of facts that I found here. One field, it's more horsepower than the first 4 rows of NASCAR. So we're talking it takes 8 NASCAR cars to equal one dragster. I mean, and it's 8,000 horsepower. Your car at home probably only has maybe 100. I mean, this thing is a lot of fuel. 11 gallons per second. Your regular engine can't even drive the supercharger, the thing that forces the air down into the engine. A normal car engine doesn't have enough horsepower even to turn that thing. The 3,000 cubic feet per minute are rammed down this thing. There's a stoichiometric mixture of 1.7 to 1 air-fuel mixture. 7,000 degrees. It says nitro burns yellow, but the spectacular white flame is raw burning hydrogen, disassociated from atmospheric water vapor from the searing exhaust gases. Spark plugs are totally consumed after halfway the engine's dieseling from compression. You can only slow it down by turning off the fuel. It would just continue to run because it compresses everything and it ignites on its own. A dragster can reach over 300 miles an hour before you have completed reading this sentence. They go 0 to 60, get this, in 0.3 seconds. It takes my truck, I think, 5 seconds to get there. In 0.3 seconds, they're already doing 60 miles an hour. Unbelievable. Including the engine the engine only has to survive 900 revolutions before it blows up. Assuming everybody is paid, the equipment's paid off, the crew works for free, and nothing blows up. Each run costs $1,000 per second. I'll leave you links to these two things if you want to learn a little bit more. But let's talk now about acceleration. In this picture right here, I've got 4 pictures, and these are what are called motion diagrams, a series of pictures taken at equal time intervals. And this one here, if you see the person standing still there, that means there's no motion. So the velocity here is 0. Here you're seeing them at equal time equal spacing, so they're moving at a constant velocity. And then this letter C, you'll see that they're getting farther and farther apart. So here, you're accelerating. Here it looks like you're getting closer and closer together. We call this decelerating. Or slowing down. It's another way to say decelerating. I've got a couple of definitions that I want to get through. And what I did is I want you to draw parallels between what we did last chapter with velocity. We already know the definition of velocity. It's your displacement, how fast you're going. Your displacement divided by your time. Or your change in displacement divided by your change in time. Now, that's something that we learned last chapter. I want you to see what the definition of acceleration it is. It's your change in velocity divided by your change in time. It's how fast you're getting faster. How fast you're getting faster. How fast you're accelerating. Like when you step on the throttle, you'll notice like your speedometer on your car goes up, or you step on it harder, the speed changes quicker. Now, average velocity, we defined average velocity last chapter, and I'm just going to put this bar over top of it to denote average because that's kind of what it's for. The average velocity is your final displacement minus your initial displacement over your change in your time, your final time minus your initial time. Sometimes we call this your delta, your change in displacement over your change in time. Look at the definition of the average acceleration. Your average acceleration, it's your final velocity minus your initial velocity, or how much your velocity has changed in how much time. Remember when I talked about stepping on your gas and it goes up very slow? So how long does it take to go from 0 to 60? Or you step on it and you go a lot faster. How much time did it take to go from 0 to 60 there? Your instantaneous velocity, we define that as the slope of the tangent of the position versus time graph. So we had a position versus time graph, your displacement or position versus time, and you have maybe a graph here. And we would take the slope. Now the instantaneous acceleration is the exact same thing. It's the slope of the tangent of your velocity versus time. So you've got a velocity versus time graph, and you'll notice your velocity is getting a little bit faster. Take your point, find your slope. That's the instantaneous acceleration. So there's a lot of parallels between these, between velocity and acceleration, what we learned last chapter and what we're going to learn this chapter. Now, the next thing I want to talk about is both positive and negative acceleration. Velocity and acceleration are two different things. You can be going this way and accelerating that way. You could be going this way and accelerating this way. Just because you're traveling in one direction doesn't mean you're accelerating in that direction. So here's what I want to talk to you about first. So in this first case, your velocity, it looks like you're traveling in this direction. You begin over here and you end over the right. And you see how you're getting faster? You're also accelerating in this direction. This next one, you start on the left, you end on the right here. You're still traveling in this direction, but when you slow down, that means your acceleration is in this direction. You're going this way but accelerating that way. That's deceleration. In this one here, your velocity, you're moving to the left. You're traveling to the left, so your velocity is to the left. And you're also getting faster. In this last one, you're traveling to the left. And you're also accelerating to the left. Oh, I'm sorry, you're slowing down, which means that you're accelerating to the right. Whenever your velocity and your acceleration are in opposite directions, we call this slowing or decelerating. If ever they're in the same direction, that's speeding up or accelerating. Looking at these graphs, velocity versus time graphs are really confusing because if you treat them as if they were position versus time graphs, they get really tricky. Let me give you, for instance, this first graph right here. This means that you're going at a constant velocity east. Just like this one here is going at a constant velocity west. I can tell right now which one's going faster because this one's farther away from the axis or 0 meters per second than the other one is. Now all these other three are all changing directions. Or not changing directions, but they're changing speeds. So as time goes by, their speed is either getting bigger or getting smaller. Let's look at letter C first of all. You start out going west very fast, and then you end up stopped. So you ended up you're going west the entire time because the line is always above 0. So you're going you're going east. I screwed that up. You're going east the entire time, but then you slow to a stop. So you're just going east, slowing down. This one right here. Kind of the same thing, except you start off at a standstill, and then you end up going very fast. So here you're going east, speeding up. And this last one, this one is tricky. You start out going in the east direction very, very fast. I'm sorry, west. I get screwing this up. You start out going west, and then you stop. And then you change directions, and you start going east very, very quickly. So you're going very, very fast, and you slow down and stop, and then you travel going east very, very quickly. So here you're decelerating. Here you're accelerating because your speed is getting larger. Here you're stopped. This one's a tricky one. It's probably best described like rolling a ball up a hill. You roll a ball up a hill, it goes very, very fast to begin with. It stops instantaneously and then starts rolling back down the hill. A couple of examples and then we're finished. Example 1, it says refer to this graph and then tell me what's going on. It says find the average acceleration. So from 0 to 5 seconds. So here's 0 seconds. Here's 5 seconds. Remember, average acceleration is your change in velocity over your change in time. So my final lot was 10 to 0. So my change in velocity was 10 meters per second. And the time was 5 seconds. So this is 2 meters per second per second. So I'm getting 2 meters per second faster every second. And we write that like this, meters per second per second, meters per second squared. These are the units of acceleration. So from 15 to 20. So here's 15, here's 20. My change in velocity, it looks like my final is 4 to 10. So 4 minus 10 is negative 6. My change in time was still 5 seconds. So that's going to be negative 1.2 meters per second per second. So I'm getting 1.2 meters per second slower every second. And so 0 to 40, I start here, I end here. My change in velocity is 0, 40 seconds. That's 0 meters per second per second. Now I'm ignoring a little bit of significant figure stuff here just for the sake of understanding this. But everything probably should have, looks like, 2 significant figures. So 2.0 for this one. Now what's the instantaneous acceleration? Remember, the instantaneous acceleration is the slope of the tangent line at 10 seconds. So here's 10. Right there, that slope is 0 meters per second per second. At the 17-second mark, so here's 15, 16, so right here, my instantaneous acceleration right there, it looks like it's going to be the slope of this line, what we did from 15 to 20, which was 1.2. So this is negative 1.2 meters per second squared. And then at 35 seconds, here's where you're going to see it's a little bit trickier. So here's 35. So it looks like my tangent line goes like that. And if I'm real good, it looks like it goes down, that's down 2 meters per second as it goes 5. So I'm going negative 2 meters per second, because that's what this is, meters per second. I'm going rise over run, down 2 in 5 seconds. So that's negative 0.4 meters per second per second. So the difference between average acceleration and instantaneous. Average is your final minus your initial divided by your time. And then instantaneous is that slope. Just like back in the velocity days, the average was your final minus your initial divided by your time. Your average is final minus initial. And the instantaneous velocity was the slope of the tangent. So is the instantaneous acceleration. One last example problem, and then I'll let you go. It says, describe the motion of a ball as it rolls up a slanted hill. So I've got a ball going up a hill. It starts at 2.50 meters per second. It slows down for 5 seconds. Stops for an instant, and then rolls back down. So notice how I made a picture. That's what you should do in every physics problem. Draw yourself some sort of picture to model what the words are saying. It says the positive direction is chosen to be up the driveway, so I'm going to make positive up the driveway. The origin is at the place where the motion begins, so here's where we're going to say where the origin is. It says, what is the sign of the acceleration as it rolls up the driveway? So as it's going up the driveway, I'm traveling in this direction, but I'm accelerating in that direction. I'm slowing down. So for this first one, I'll just call it part A. What's the sign of the acceleration? That's going to be negative because it's accelerating downhill. Part B, what is the magnitude of the ball's acceleration as it rolls up the driveway? Remember, your acceleration is your final velocity minus your initial velocity over your final time minus your initial time, or just your change in velocity over your change in time. So my velocity changed. My final was 0. It stops. My initial velocity was 2.5. My time that it took me was 5 seconds. So if you'll notice, 0 minus 2.5 is a negative 2.5 over 5. So that's negative 1/2. And that should coincide with part A. And my math should match what my sign convention says. I know this was a little bit long, and I tried to power through it, and I appreciate you sticking with me. But it's really important to know the difference between average acceleration and instantaneous acceleration. And average acceleration is just your change in velocity divided by your change in time.